Okay. Good. So good morning. On Wednesday we finished looking the some. Let me put this down. I'm too short. So on Wednesday we finished looking some nucleophile that can give hydride to the alkyl halides. And now we are going to see in this class some other nucleophiles that you can use to make a nucleophilic substitution. Okay, so the first one is the oxygen nucleophile. And in this one, you have a typical reaction, which is So this is the typical reaction with oxygen nucleophile, which is the Williamson ether synthesis. So you basically use an alkoxide, which can be also an aryl oxide. So this can be an alkyl group, okay? Any alkyl group, or this can be also an aromatic group. Usually you form this, by the addition of some base to alcohol, okay? So basically, you start from the alcohol, you generate with the base the alkoxide, and then you treat that with an alkyl halide. And thus give you by an SN2 reaction, give you this compound, which is an ether, plus the leaving group. Okay? So this is the most typical reaction that we can use with oxygen nucleophile. Now, of course, if these groups are the same, then you can have a symmetrical ether. And if these groups are different, of course, you can have a non-symmetrical ether. Okay? So you can play with these two groups as well. There is a variation of this reaction, which is when you don't have, imagine that you don't have, we will see this in another reaction now, but if you have two different alcohol, okay, and you want to generate an ether, in this case, any idea what do you have to do? So in this case, you have two alcohol, right? So the first step here will be to transfer, for example, one of them to a good leaving group. Okay, we will see that reaction now. For example, a tosylate. Okay, now this one is pretty much similar to this one. Okay, so now this can again react with this one and give you the ether. So, but basically the concept is the same, right? So you have a nucleophile, and then you have an electrophile. In this case, you have the alkyl halide. In this case, you have another alcohol, but is now suffer a reaction to have a better leaving group here. Okay, but the concept is the same. Another thing that you want to keep in mind is that anything that can help you, and this is just one example, but anything that can help for the leaving of this group here will be a good thing for your reaction. Right? So for example, if you have, and this is another reaction that we will see now, a chloride. This is not an excellent leaving group. It's a good leaving group, but it's not the best leaving group. So usually what the people do is add a little bit of potassium iodide, and that will exchange this chloride by the iodide, which is a better leaving group. Okay? So, and this, you can do it in catalytic amount, so you don't need to add too much of this, because this will replace this chloride also by a nucleophilic substitution, and then this one is the one which is more reactive, will react with the alkoxide, okay? And this is another type of reaction that we will see now. But everything that you can do to help the molecule that contains the leaving group to react faster is good. For example, another thing that you can do is there is some salt, like for example, silver and oxide, that can coordinate. For example, if you have alkyl bromide or alkyl chloride, you can have something, a coordination like this, in which now this is more weak. Okay, so now this will react also faster when you put in the presence of an alkoxide. Basically, the three things are the same. So you are trying to improve the leaving group for reaction with the alkoxide. Is that clear? Okay. So there is, of course, you have to keep in mind as well that there is, in this reaction, the elimination is also a side reaction that can happen. So you know that when you study the competency between elimination and substitution, the temperature, the solvent, the concentration, and everything, the nature of the substrate is important. So you have to keep in mind that the E2 elimination could also happen. So then this is the most typical oxygen nucleophile. Remember, alkyl or aryl alkoxide with the alkyl alide. So, of course, this is an SN2 here, which means that normally this reaction works pretty well when you have a primary alkyl alide. Okay, so this can work also sometimes with secondary, but not with tertiary alkyl. That's clear, right? Okay. So this reaction here, when you have an alkyl alide like the chloride, and you exchange one of the atom, one of the alide, by another one, this has a name which is so this will be kind of halogen nucleophile, and this reaction is the Silken. So this is most of the reaction that you have studied in this chapter has been discovered by German chemists. So let's see which is the next one that any of you will discover. So this is also a German chemist that discovered this exchange of alides, and it's as you can imagine, this is an equilibrium reaction. Okay. So this is an equilibrium. But if you take advantage of the different solubility of this salt, then you can drive the equilibrium to the right. So I put you an example. So if you take this bromoethane and you react with sodium iodide, this, if you make the reaction in acetone as a solvent, this is soluble in acetone, this is soluble in acetone, this is soluble in acetone, but this one precipitates in acetone. Okay? So that means that now the equilibrium is shift now to the right side of the equation. Is that clear? So are you agree with this? Any comment? Any thought? Nothing? Are you hungry? Yes. Okay. So this is the typical reaction. As I say, don't forget, this is an equilibrium reaction. Okay? but you have to think about what is the best condition to drive this equilibrium to the right. Okay? So what else? So the best, again, are the primary alkyl halides. Secondary sometimes works. Tertiary does not work in this reaction. Okay? So basically, primary alkyl halide. So an expansion of this reaction is also this one here, okay, in which you transfer the alcohol in a tosylate, which is a better leaving group than the hydroxy, and then this one reacts with the alkoxide. This is basically the same concept than that one as well. So if you take this here, which has a very good leaving group, basically, as you see, there is almost no difference between this one and this one here. Both has a good leaving group. So if you put this with sodium iodide, this will also make the reaction here, okay, and give you the alkyl halide. So have you studied already the chemistry of the carbonyl group? Have you studied that chapter? Chemistry of the carbonyl? Yes or no? Okay. So then you will study that, I think, later, and this is relevant for when you study that. There is another type of nucleophile which is very important, which are the phosphorus-containing nucleophile. This is more important in the chapter of the carbonyl. So when you study the chemistry of the carbonyl, you will see that because there is a reaction which is very famous. So this reaction, I put you an example here. So this is the Beatty reaction in which you use an aldehyde or a ketone, and then you generate an alkane. Okay, and this is the phosphonium salt that you use. So you will see that in detail when you study this carbonyl chemistry. But this is also important because this can also react, it can have a role in the reaction with alkyl halides. So basically, if you take triphenyl phosphine, for example, and you react with any alkyl halide, it will give you the corresponding phosphonium salt. So this one is also an SN2 reaction. Okay, triphenyl phosphine with the lone pair here, with act as a nucleophile, with the alkyl halide, gives you the phosphonium salt. Okay. Now, when you have this phosphonium salt, if you treat this with a strong base, like for example LDA, any strong base that can deprotonate this acidic proton here will give you this, which is actually and ylide. So this is the Wittig reagent, okay? So you are using an SN2 reaction to fabricate the phosphonium salt, and then this is treated with a base to fabricate the reagent that you use to make the Wittig reaction. So when you have this one here, okay, imagine you have a phosphonium salt like this, okay? So this is a resonant, so you can have the two chair on the carbon and the phosphorus, or you can have the double bond, right? So this is a nucleophile here. So this will react also with any alkyl halide to give you the new salt. Okay? So as I say, these phosphonium salts are important but not very useful the people don't use that too much in the chemistry of alkyl halide, but they use a lot in the chemistry of carbonyl. So you will study that in more detail later. So basically you have so far the hydrogen nucleophile, the oxygen nucleophile, the halogen nucleophile, phosphorus nucleophile, and which are, do you know any other that is very famous as a nucleophile? So any idea? Nitrogen nucleophile, right? So you can have the, let's see if I can make this. So nitrogen nucleophiles. So here we have at least 3 typical examples of compound that can have a nitrogen. So let's say the first one are the acyl group. Okay, so these are this type of group, and this can be either inorganic, like for example sodium acyl, or organic, that will be something okay, so this is the acyl group. If you have an organic part, you will have that one, and you have this nucleophile here. Okay, so this is a charged ion, so it means that it's a good nucleophile. So it's not the best nucleophile, but it's actually better than, for example, ammonia, which is neutral. So if somebody asks you which is the better nucleophile, you have to think about you have charge negative here, which make a better nucleophile. Okay, so this is much better than this one, although it's not the best nucleophile. This organic acyl, you will also see that later in your study. These are sometimes explosive compound. So this, depending on the size of this compound, the molecular weight, this can be explosive. So you have to be careful when you work with this compound in the lab, but you will see that later. Just keep in mind that this could be somehow a little bit, you have to have a Gaussian working with them. This can work in nucleophilic substitution, both in aliphatic and aromatic system. Okay, and for example, this one here. So this is the way that you make the sodium Si in industry. So you take nitrous oxide and you treat it with sodium amide, and you generate the sodium Si. That's the way you fabricate that at the industrial level. So there is the important thing about this nucleophile is that you use this nucleophile to incorporate an amine group in your molecule, okay? For example, you can start from an alcohol and finish with an amine compound here. So this is the nucleophile. Then you need another reaction. Once you introduce this one, you need another reaction to transfer this to the amine, okay? But now the most important is the first reaction, how you introduce this one into an organic compound. I will put you an example here. So these are the same group, so I will not write. You know what is this compound? Any of you know that? This is an amphetamine. This is how you synthesize amphetamine. I'm not saying you should synthesize that, but this is the way that is making. So a hydroxyl compound like this one is transferred in the amine compound. Now we will see this. The name, if you look at this compound here, so the name of this compound is alpha, okay, methyl, phenyl, amine. Okay, this is how you make amphetamine. A-M-P-T-A came from the name of the compound. Okay, so how you make this? How you make this molecule from this alcohol using Si as a nucleophile? The same thing that we see before. This is not a good leaving group. So the first thing you do is transform this into a better leaving group. So I will just put the aromatic. Now, this one, so react with the tosyl chloride, for example, and make a tosylate. A much better leaving group. And this one now can react with the Si in a SN2 reaction, okay? And this will give you this one. Now, the other day we saw what is the stereochemistry of the SN2 reaction. If for you is important the stereochemistry here, then you should use this route. Why? Because you can control the stereochemistry of this center. So you made this reaction, the stereochemistry here is the same. Okay, but when you do this one, the stereochemistry here now is inverted. okay? So, but it's a chiral compound. If you don't care about chirality, then you can just directly treat this one, for example, with ammonia, a very weak nucleophile that therefore react via an SN1 reaction. Okay, so here is an SN2 reaction that you have to use if you care about chirality. If you don't care about chirality, you will generate a carbocation here, treat it with ammonia, will give you also the final compound, but in this case will not be chiral, will be racemic. So you will get a racemic product here. So it depending on what you want, okay? But just keep that in mind. Another type of reaction. So another type of nucleophile, of nitrogen nucleophile, are the amide, okay? And these are the typical reaction is the Gabriel synthesis. Another German chemist, Sigmund Gabriel. Sorry, I forgot to tell you here. Of course, I told you that you need another reaction to transfer this side into the amine here. And this normally is not for this chapter, but normally you do that by hydrogen in palladium. Okay, so this is the condition to transfer, for example, one of the conditions you can use to make the transformation of Si into imine. Is that for me? Okay. So the other important nucleophile is this imide, and the typical reaction is the Gabriel synthesis. In this one, you use an alkyl halide, and then you use an phthalimide. Okay. So in this case, again, you start with the primary, normally with the primary alkyl halide, and you finish with an amine. So you use phthalimide, okay, which is also a nucleophile. For example, potassium phthalimide, that is also a nucleophile in the nitrogen. So this one reacts with the nucleophilic substitution and give you this intermediate, which is now non-nucleophilic anymore. So this will not react anymore. Okay, this is a stable. Now, with treatment, for example, of hydrazine, like this one, you can break this molecule and form the amine. Now we will see that how that happens. But this is you can use this, or for example, very strong basic condition like sodium hydroxide, and you can get the free amine. Now, how that works? Okay, so I have to go a little bit fast, but basically, normally you have the neutral phthalimide, okay, that you treat with a base to generate the anion here. Okay, now you have the nucleophile. This react with this one and generate, actually, let's put here So this molecule is stable. And if you see this nitrogen, this lone pair here can be stabilized with different, either in this side of the molecule, either in this side, you can have resonant structure like this one, okay? And the same thing in the other carbonyl. So that's the reason why this is stable, okay? This nitrogen can be delocalized in this amide group. So when you now treat this with a nucleophile like this one, for example, then this can attack the electrophilic center in this molecule. And the electrophilic center now here is only the carbonyl, okay? So another nucleophile can attack here. And if you attack here, you can break this part of the molecule to the carbonyl and then break this part. Basically, that will give you this molecule, and now you have another nucleophile here that can do the same thing in the other part of the molecule. So of course here I know writing, but I guess you know that in some of these steps you need an exchange of the proton, okay, to neutralize the different amines. But this one here will give you the amine part, okay, and this cyclic product here, and this is very stable. Okay, so this is how it works. But basically, what you have to remember is this is also a nucleophile that can be used to introduce amine groups into any organic molecule. Usually, you use primary alkyl halide. So, of course, there is also so this class is until 10, right? Until 10? Okay. So this class finishes at 10? Okay. No, it's okay, I can write this. You cannot read? So let's see. If I write here, you don't see anything? No, it's okay, but the other part, you are still right, but you are recording this, right? You can see later, right? Okay, because if you look at the other and you don't look at what I'm saying now, then you will not see this one either, right? Okay. Let's see. This one? Good. Just let me know when you want to stop. Good? Excellent. So now let's go down with this one. Okay, guys, the last one of the nitrogen. The amine. So these are good nucleophiles, right? You should know that already. I think this is quite obvious for you guys. So this is a nucleophile. Why? So if you look at the periodic table, which is the group in which the nitrogen is? Which group of the periodic table? Okay, group number 5. Okay, so that means you have how many electrons of valency? You have 5 electrons, right? 1, 2, 3, and then you need 2 more. Okay, the nitrogen is more electronegative than anything that is attached to it. You have a lone pair, therefore it's a good nucleophile, right? So you have this one now, and this is usually used to synthesize ammonium salt. It's very difficult to stop here. For example, if you want to do monoalkylation, imagine you use bromoethane, for example. Okay, so this part here are the new ethyl group here. It's difficult to stop here, for example. You know why? Because now this, when you do the first alkylation here, this product is also a good nucleophile, right? So if you have more bromoethane in the reaction, this will react again with the bromoethane, okay? And like this, you can have, if you do that yourself, because we don't have too much time now, and I need to explain another one. If you do that several times, you get at the end this ammonium salt. Okay, so keep in mind that when you use an amine, this is very nucleophilic. It's difficult to stop in the monoalkylation, so the reaction keep going, and therefore, if you look at in your reaction, you can have a little bit of the starting material. If the reaction is not complete, a little bit of monoalkylated, a little bit of dealkylated, a little bit of the ammonium salt. So this is a very complex situation, so you have to be careful with the imine. So of course, this is, I put here an SN2, but this also can react with via an SN1 reaction if you have another electrophile, like this one, that can generate a stable carbocation, like this. Then the reaction will be an SN1, right? So the same thing for all the nucleophiles. So, and the last group of nucleophiles, which is also important, and this one also, you will see that later in the chapter of the carbonyl group, like the Wittig reaction. These are also very important there. So there is again four, let's say 4 group. You have, for example, this acetylide. This is also a nucleophile, okay? This can also react, of course, with the alkyl halide, okay, to give you the introduction of alkene groups in your molecule. Now, this is a very strong base. This is like 1 billion times stronger than sodium hydroxide. What that means? That means that this is usually limited to a primary alkyl halide. So if you use a secondary or tertiary, because this is a very strong base, you will have elimination as well. Okay? So basically limit to the primary alkyl halide. Another, I know that you already have studied this organo lithium and organo magnesium, and this usually does not react with alkyl halide, usually, okay? But in some example, you can see this as well. So this is also a nucleophile and could react also with this alkyl halide to give you alkane. Then you have another one which is nitrile. So this is what is called this ambidentate nucleophile. Okay, here you have a negative chair in the carbon, a lone pair in the nitrogen. So both of them are nucleophile. Okay, now you have studied already this concept, right? The soft half. So, which is the soft part here? Carbon or nitrogen? Which one? Carbon is soft? Are you all agree with that? What do you think? Carbon is soft? What do you think?
I think nitrogen is the soft part because it's more electronegative than
No, you are right. You are wrong. Carbon is the soft. So look at that again on this part. Okay. So that's the soft, and then you have the hard. Okay. Is that correct? By heart? That's all what I have learned in 2 years. Okay, so that's the soft part, that's the hard part. Okay, that means that depending on now on your substrate, this can react either here or either here. For example, so now if you have an SN1 reaction, for example, with terbutyl bromide, this will react with the nitrogen as a nucleophile, okay, with this part, which is the hard part, okay, and this is the hard center. So if you use, for example, ethyl bromide with another, this one, via an SN2 reaction, so this is terbutyl, primary alkylamide. This now react with the soft center here, okay? So this part here is soft. And this will give you a different compound, which is a nitrile. So either you can generate isonitrile or you can generate nitrile depending on this soft-hard theory. Okay, so and then we have another one, which I will have just 1 minute. So another group, and also this one you will see that later, are the enolate. So the last group of the carbon nucleophile are this group when you have an activate methylene group in either ketone, aldehyde, or ester, then you can generate an anion here with a very strong base. Okay, and this is the nucleophile that can react with the alkyl halide. Of course, here is still a hydrogen. So if you treat this with more base, then after the first alkylation, it's possible also that you generate another anion here, okay, like with more base, and this one react again to give you a dealkylated product. Imagine that, for example, your group here is a D-alide. For example, bromide, a chain here, anything, 4 carbon, for example, and another bromide. What could happen? Now, the first reaction takes place here, and then in this group here, you can have wherever it is here in the middle, and you still have one bromide, which is a leaving group. So if you generate another anion here, this can now attack here and generate a cyclic product here. Okay? So what I want to say is keep in mind all the part of your molecules. So if you have this, you have 2 electrophilic centers here, 2 possible leaving groups. So if you do the reaction with one, and then you have another anion or another nucleophile in your molecule, intramolecular can happen this reaction as well, which is another SN2 reaction, but in this case is intramolecular. Okay, and then you generate a cyclic product. So I think I don't have time for that, but you may think that this, when you generate this anion here, so you know that's resonant equilibrium, right? So again, you have the soft here and the hard center here. So the fact that you obtain a C alkylation, so that this molecule react here, or this molecule react here, will depend again on this, where we have this soft acid-base, hard soft acid-base theory. Okay, so remember this anion here is a resonant structure with these 2 here. And therefore you have a nucleophile here and you have a nucleophile here. Both of them could react, but only thinking in this theory, you may think if you have a soft alkyl ally, this one will react here. If you have a condition to have a hard center, will react here. I think you will see that more in detail with Oliver. But that is important, okay? And there is also another important thing, that is, this is symmetrical. So it's the same this anion here that this anion here. But if you have something like this, the anion here is not the same like the anion here. So depending on the condition in which you work, you can generate the anion here or you can generate the anion here. Okay? So a lot of stuff, but I think this one will actually be covered later. I was told I should give this in this time, so I'm sorry it was too fast, but is what it is. This was my commitment, so I hope that if you don't understand anything or anything at all, then you can stop also by my office and we can discuss more in detail. So I don't have any problem on that, but that was what I could do. Okay, thank you.